Cool. So we have 30 minutes for education session from Scott. And then as usual, at the top of the hour, folks will usually stay on if they want to do any water cooler conversation. Unfortunately, once again, I will have to drop at this top of the hour. Sarah, putting you on the spot as usual. You'll be able to continue to do that. Okay, so I know most folks here know Scott, and Scott's been on the calls before, and Scott's no stranger to the open standards world. I think I'd say decades of experience and and really shaping, I'd say, the interoperable ecosystem for geospatial. And I have a personal gratitude here for Scott in that 3D tiles, the OGC community standard that is one of the bridges of 3D between like the Chronos and graphics world and the geospatial world. It was Scott who convinced me and said, hey, OGC would be interested. And we had this community standard process. And Patrick, you don't know me yet, but you should come talk to OGC. And this was probably 2000, I don't know, Scott, 2016, 2017.
Yeah,
And
maybe even earlier. Yeah.
and
Yeah.
you were right. You were so right. That was genius. Thank you for that. So Scott is the Chief Standards Officer at OGC, and we're going to hear about the latest of 3D within OGC. And I think there'll be some things familiar and some things that's new and exciting to us. So Scott, all you. I'll stop the screen share and please share whatever slides you have.
Good lords. Want me to share all sorts of fun things. Here we are. Great. Thank you, Patrick, for inviting me again. And thanks, everyone, for hearing me out today. As noted, I look after the standardization activities in OGC. And so today I'm going to do a bit of a refresh of some of our activities in 3D. In particular, I've talked to this topic a number of times with SIGGRAPH and Chronos group and in other parts of the Metaverse standards group. So, but there's some new developments I want to cover. And I'll preface it as well as I'm kind of hyper keen on 3D, to say the least. Prior to joining OGC staff about 11 years ago, I chaired most of the 3D related working groups inside OGC and did so for more than a decade before that. So I'm not allowed to have favorite standards and activities in OGC, but clearly 3D is by far my favorite stuff I work on. And so hopefully you'll see that as I go through this. I want to sort of break this into four major topics, some basic information and foundation, talk about the data models, getting data to the users, and then ultimately what we'll be doing in the future. This presentation does talk about the real world. We are going to look at how you bring real world, the natural or the built environment, into 3D, model it in 3D, and therefore it's really messy. We all know how messy the world is. There's complexities in modeling the real world that probably none of us think about. None of us should probably ever have to worry about, but they're real. So some of this foundation may seem a little odd at times, but you'll see how it builds. That being said, if it's just too intense, if you can't handle all this real world stuff, just go to your browser, open up YouTube, search for Dr. Tung's 3D House of Cats, or 3D House of Beef, or 3D House of Stewardesses. Watch those enlightening, true 3D movies and come back and join us in about 20 minutes. So, what are we in OGC? OGC is a group of more than 500 organizations from government, industry, and the research and academic community dedicated to making standardized interoperable solutions for managing location, geospatial data. We want to make those data fair, findable, accessible, interoperable, and reusable. We develop standards, but we also operate a testing facility, if you will. It's a applied research and development arm that actually performs projects to test these standards in real world scenarios and ensure that when we publish a standard, it's going to work, it's going to be implementable, and that the community is likely to accept it. If industry won't adopt one of our standards, it's completely useless, because if the industry won't implement it in their software, who's going to ever get to use it? So we really do not just look at hypothetical standards. Some of the stuff you'll see today may feel hypothetical, but it's not. It's all quite practical. You've got one of these. There's a bunch of mapping apps on these things. All of those mapping apps underneath, deep under the hood, have one or more OGC standards in there to ensure that the map information shows up in the correct place, rendered the right way, and gives you the correct information that you need. So let's start with the basics. What are those underlying standards that underlie the phones in 2D or 3D? In OGC, we have a rather large portfolio of standards to choose from. Andrew Tannenbaum's quote's quite appropriate, but it's a bit misleading, and it was certainly quoted from him tongue-in-cheek as well. We focus on ensuring that our standards are highly modular, highly specialized, and that you can plug them into each other so you can combine standards to solve a problem. So as you look at this architecture, which you probably can't read on your own screens, you'll see there are a lot of very specific standards that solve one little piece of a problem. And you just bolt these together to build your bigger solution. And so as we talk through the standards today, you'll see I'll be highlighting a variety of these from this architecture. Fundamentally, underlying everything, we have to have a representation of these real world objects. Today, I'm going to talk about what we refer to in the spatial community as feature data. A feature is a computer graphic representation of a real world object by vectors. They could be points, lines, polygons, curves, surfaces, solids, but a feature is a geometric representation of this real world object. We also have an entire suite of standards to represent volumetric continuous data, like the atmosphere and the ocean, et cetera. I got another 20 minutes for you on that another day, but we're not going to talk about that. Today, we're going to focus more on features. And of course, I have to throw in a little UML because otherwise I'm not a standards guy if I don't do so. But underlying it all is a very simple geometric model that was developed with OGC and the ISO community. It forces data into a fairly simple geometric representation, realized in a couple of standards like KML or simple features. And then with 3D geometry, we can go on to a foundation standard we refer to as GML, upon which we built others. There are other ways to get to 3D, and we'll be talking about that at the end, but that's the general approach. So KML, many of you are probably familiar with. Google purchased Keyhole, Earth's Viewer, years ago, and they had the Keyhole markup language. Google converted that just to KML. And back in 2007, assigned the intellectual property for KML to OGC, and we took over management and maintenance of KML. KML is a really simple 3D Earth-centric standard. Like psychotically simple. I'm an idiot for development skills, and I can write KML by hand, so it's really not that hard. Very simple, but as being very simple, it doesn't do a lot. The geometry of KML is basically a footprint of something and extruded. That's your 3D of your native geometric objects. You can insert 3D models, say Collada files, into your KML scene, but very quickly it becomes overwhelmed and non-performant. There are some degrees of levels of detail. You can portray some other interesting attributed data that's related to your objects, but it's fairly straightforward, fairly simple, and has a single coordinate reference system, so somewhat limited in what you can do. The far more complicated model that we have is something referred to as a geography markup language. So this is an XML-based representation of all types of geometries, 2D, 1D, 2D, 3D, and their topology. So understanding objects that are adjacent to each other or intersect each other, et cetera. A BREP approach to any of the 3D geometry, very, very sophisticated handling of coordinate reference systems, which will be important in a moment. But like I noted, it's very, very complex. Virtually no one. I think there are 2 softwares in the world that implement the entirety of GML. Most people use application profiles. We're going to go through a number of these, but things like City GML or Indoor GML. That GML batch, that's the underlying geometric engine, but they've been profiled to solve very specific problems. But that complexity is really important. So this is the bit that you probably don't think about, and why you need people like OGC behind the scenes. If you were flying from San Francisco to northern Japan on March 11th in 2011, your airplane missed the runway upon landing if it was using just GPS, because Japan moved 6 meters closer to California in 3 minutes. I mean, yeah. So understanding that this is going on the Earth every day, all over the planet, and there are ways to handle these kind of changes and do so with proper, rigorous standards is really, really important. And that's why under the hood of a lot of the work that we want to do when we're representing reality in a metaverse type environment should be able to support these complex abilities to represent what really happens in the Earth. And so that's why some of our stuff is so complicated. So let's jump into then some of these data models that are modeled and have that ability to handle some of these complex aspects. I like to refer to our data models as useful digital twins. I don't consider a digital twin to be a digital replicant. It is not a full exact 3D and chemical representation of the building. Rather, when we look at digital twins or creating 3D representations of objects from the real world, we also tailor those to serve specific needs and purposes. And so they are somewhat optimized and somewhat simplified to represent just what needs to be done with those models. We have City GML, Indoor GML Buddy, and CDB that I'll talk about. And there are others out there in a variety of formats. So let's jump into these and I'll explain sort of how they relate. So City GML, as you might suggest, is a city model language. It is a way to describe the objects you would find in a city: buildings, trees, streets, curbs, everything like that. At the moment, it has 3 encodings, 2 of which are OGC standards. The GML encoding, which is also called City GML. Yes, I know that's confusing. Yes, we do have a branding issue. Yes, we're trying to fix that. But just for now, bear with me. City GML is a conceptual model for modeling a city, and you can see it in XML. You can also see it in JSON, City JSON, which is one of our community standards. I'm going to talk more about those in a bit, but a standard developed external to the OGC that we've adopted, and then a database version of City GML. What it is fairly simple set of models that describe the real world. So you see down at the bottom the kinds of things that you represent: buildings, bridges, etc., but also the land use, vegetation, water bodies, and then some applications that you can perform on top of the data. This is a change in our latest version to make these city models far more useful. They originally were quite simple in that it represented the 3D data of a city in XML. It was very heavy. Computational capabilities at the time left it mostly as an data interchange format. Now, with better computational abilities, better encodings, et cetera, we can do a lot of work directly on the city model. And so we've added some things for dynamic data, versioning, point clouds, et cetera. And then revise a few of the other key aspects based on real world implementations. An example here in Berlin, there is an atlas for the solar generation potential for the entire city. And these building models also include information about their insulation, so their thermal capacity to hold heat or cooling, as well as their geometry. And so you can optimize what rooftops are best to put on solar panels for solar power and which buildings need the power the most. So you optimize the location of where you put those panels. All modeled in the city model, all modeled in real time. Singapore has a full 3D city model now in City GML, and you can also download one for New York City from the Technical University of Munich with more than 1 million buildings in a variety of levels of detail. Some of these levels of detail, as you see here, are quite simple, just simple building extrusions. But City GML also supports high levels of detail, including interior aspects of the building, such as the furniture, the faucets, whatever you might want to do. City GML is 2/3 of the way to building information models, BIM. So if you're familiar with BIM data or industry foundation classes, the IFCs that you model BIM, that's even more sophisticated, but City GML and BIM data are somewhat interchangeable, and the level of detail are quite similar in many cases. We held a challenge a few years ago looking at some new novel uses of City GML. There is a report on that on the OGC website. I forgot to put the link on the slide. I apologize for that. But go to our website and look for those results, and you can see some great use cases of City GML now. More than 1,000 municipalities in Japan work with City GML data, as do a number in Germany, as I noted, Singapore, several cities in China. It's becoming quite widely adopted. As I noted earlier, there's also a JSON flavor called City JSON. It's a little simpler. It does have the complexity of modeling the last 2 versions of City GML with slightly inconvenient versioning paradigm, but too bad for that. But really great lightweight way to build city models in JSON. So much easier, obviously, for your coders and much easier for a lot of the users. City GML can also form the foundation for indoor modeling. And so we have an indoor GML, which is City GML geometries, giving you the description of the building and its interior spaces, and then a co-referenced network that lets you determine navigation through those 3D objects. And so it's effectively a graph that lets you decide, are these 2 rooms connected? Are they connected in a way that can be navigated on foot, by a wheelchair, by a drone, whatever else it might be, and allows very sophisticated indoor modeling and indoor mapping. also built on CityGML. We also have new work to solve this little problem. What does it look like underneath the ground surface? We've talked about all these buildings, all these other objects, and we've created a new standard, the Model for Underground Data Definition and Integration, very conveniently named to call it MUDDY, since it's modeling the underground and all those nasty things under there. A very, very complex model, clearly, because you have to model type geometries such as all of your pipes and other underground objects that are man-made, but you also need to model those in the real world. So you have to integrate three-dimensional geologic data and hydrologic data and other types of information. And the MUDDY conceptual model lets all of those data be fused. So you can have a very, very high fidelity representation of your underground earth. One of the use cases that's been driving MUDDY, and a lot of the work done that, is really from an AR perspective, using these MUDDY models for real-time construction and utility locating. And finally, to talk about some of the models we have something called CDB. It doesn't stand for anything anymore. It used to, but I'm not going to tell you what that was because it will just confuse you. But CDB is a container for a variety of types of 2- and 3-dimensional data that has a really sophisticated level of indexing and correlating amongst the data sets. And in fact, while it's very complicated and comes out of the military modeling and simulation community, it is a very early metaverse in of itself. It is a full, authentic, virtual representation of the real world for training military simulation. And CDB does include a lot of the other standards in its own support. I'm going to talk a bit more about some community standards in a moment, and they've all worked with CDB. So basically, you take your map data, some moving feature data, and you need to make a video game worthy representation of that real world. CDB you see in many, many flight simulators. So all the flight simulators built by CAE for Boeing, Airbus, and a few others use CDB as the engine for the real world. And then finally, we've got to get the data to the user. So this is a place where OGC historically has not been its strongest. We're really good at all that nasty math that I've been telling you about, representing that real world, but getting it to the user is where industry has always taken the lead. And so we have a process we refer to as community standards. These are specifications developed external to OGC. So either other standards development organizations, companies, nonprofits, et cetera, create a specification that the OGC community says, we really need this as part of our baseline. We want to build more work on it. We want to integrate it with our standards. And so those originating bodies submit the ability for us to publish and count these specifications as part of our standards baseline. They retain the intellectual property and the maintenance, but we take a benchmark snapshot of that specification and publish it as an OGC standard. And so Patrick and his colleagues at Cesium really led the way with the most widely implemented of these standards now, and that's the 3D tiles standard. So 3D tiles has come in as a community standard and has been revised once in our process, but we have a few others that I'll come to as well. The community standards really are the way we can bring cutting edge work into our process, knowing that we can't embed everything ourselves. So when you look at 3D tiles, again, developed through Cesium, it was first approved in 2018 as a community standard. And Patrick's colleagues just showed off at our last member meeting OGC held in Montreal in June, integration now with Google. So bringing 3D tiles into Google's environment and synthesizing the data amongst the different sources. Absolutely just blowing me away demo. It was fantastic. And our members love to see, wow, so you're actually practicing what you're preaching. You submitted a community standard at OGC, and then you showed how it integrates with the other OGC members' own solutions and offerings and other standards. So this is like our case study of all things integration and these people outside the OGC process. Remember, Cesium's an OGC member, but they're doing this work as a business. And the business then comes to OGC as something that the remainder of the community can use. And now you'll see XYZ, every geospatial software vendor jumping onto 3D tiles bandwagon. So it's fantastic. There's a similar type thing, Index 3D Scene Layers, that came out of Esri, also approved as an OGC community standard. It's on its 4th revision coming up soon. Some similar capabilities, but also somewhat different. They're somewhat optimized for different use cases, both being somewhat widely used. But we now know that Esri is also supporting 3D tiles, and so the integration amongst these community standards will be interesting. And this example here shows you a CDB data store of a valley in California being produced through Index 3D scene layers. So you've got an OGC standard we wrote inside the consortium being now shown through one of our deployed community standards. And then finally, we have another community standard called Open Flight. This is an ancient format. If any of you heard Open Flight, I think it's on version 16 now, first created back in 1988, but it creates 3D models for assets that need to be in simulated environments. Open Flight has a huge number of implementations across the modeling and simulation community from the military side. There are libraries of every imaginable thing modeled in 3D, a relatively lightweight, simple format, but also something that's a little out of date, let's say, still highly performant. We brought it in as a community standard because it's supported in CDB, but we'd like to see other 3D modeling languages and formats come into OGC in our standard process. And so that sort of comes to my next topic. What's next? Where are we headed on these standards? Well, for one, we want to do a whole lot of that XML stuff. One, XML is torture. Two, that X is actually a huge issue. When you're writing a standard, the one thing that becomes quite terrifying is extensible. And the X in XML means that the flexibility someone has to implementing an XML-based, quote, standard can rapidly result in interoperability problems. And we found this for years now. Major issues with XML files not being compatible because of poor modeling by the implementers. So a number of our standards are starting to work with GLTF as an encoding instead of XML or JSON. CityGML is doing it now, and we have other standards working groups who've said this is the way we need to work. It's faster, it's closer to the hardware, the community is more vibrant, and it's modern. This is what we need to do. So we're seeing a lot of that. And a little bit of thinking now on the USD side. There's been a bit of work, not much yet, but it's one of the things we're thinking about, and we will try to get there soon. And so I'm happy, Mikhail, to take a question now. I've got one more slide or question, y'all's choice. However y'all prefer me to do this.
Scott, usually we do the questions at the end. So if your slide's only a couple minutes, maybe Mikhail, we could just wait till then.
I've got one fast one, then I'm done. And that is all of these 3D formats I've talked about, all these ways of distributing data to the end users. We have a glory of choices. There's too many choices. And so we've got work right now on an API to unify access to these underlying standardized deployments of three-dimensional data. And so this 3D GeoVolume is intended to be an API to allow query and request of services, the capabilities of those services. Are they going to deliver geometries to your computer? Are they just going to deliver scene graphs? As well as being able to make choices of information out in these objects, regardless of their original source format or the means by which they're served to the computer. And so having a uniform API to all these 3D sources may be of interest, I think, in the Metaverse community as a means to at least consolidate the questions we ask of our data. Whether or not the data formats are all consolidated may not be so important. But if I want to say, give me something in a temporal spatial box, it's between these two dates and it fills this volume of space, that should be a single uniform query, not one that composes differently for each one of the standards. And so that's sort of where we're wrapping things up. And with that, I'll finish. Thanks very much for your time and happy to answer questions, and already see one from Mikhail.
Yeah. Scott, just one moment, please. Scott, look, really amazing job. It's cool to see the breadth of how 3D is involved in OGC. So great job educating that. We have about 5 minutes for the official meeting where we'll do some questions, and then if folks can stay on for the water cooler, Sarah will stay on to co-host, but I'll have to drop right at the top of the hour. Mikhail, do you want to go?
Yeah. I just wanted to mention, as a member of the OGC GeoPose Standard Working Group and the reality modeling language or reality modeling working group within the Metaverse Standard Forum, this is interesting, but I believe there is like a lot of ideas that need to be demystified because I believe they are relatively complicated to understand. Because at the end of the day, what we are doing when we are talking about GeoPose or geo data in general is just transforming the longitude, latitude, and altitude into X, Y, and Z, so that we can represent it into a normal 3D system. And the thing that we are having problems with when we are trying to model this is like, how can we make this interoperable with existing systems? So at the end of the day, correct me if I am wrong, but 3D tiles is just a GLTF with a position in terms of longitude, latitude, and altitude, correct?
Oh, there's a little more to 3D tiles because it does have a spatial data structure that then
Yeah.
references the GLTF, and then a number of GLTF extensions for like fine-grained metadata.
Yeah, of course, there is a lot more. But what I want to say is that I truly believe that we have to find a way to define positions or geopoints based on latitude, longitude, and altitude values, so that it can be rapidly transformed between X, Y, and Z and this other system, so that we can make this system basically compatible already, just by including that information in a way that it is possible for any system reading, for example, USD, say like, okay, apart from having the position defined with a vector in 3 dimensions, we have this other thing, and knowing the equatorial and polar radius of the Earth, it is possible to easily create these kind of systems. The big problem is just in that conversion. And once we achieve that, we can get a much better interoperability between these standards and GLTF, USD, and any others. Just wanted to mention that is what we are having problems with, how to make it so that we can include that conversion into the system itself that reads the GLTF.
That's a great point, Mikel. And one of the goals that we have in OGC is to hide from those users that don't need to know the problems like Japan moving 6 meters in a couple of minutes. When you talk about latitude and longitude, as any of us talk about here on the phone or on this call, probably all but a couple of us think of that as being something somewhat static, but it really isn't. The world's far more complicated. So we've written standards to hide that, let that problem go away. If so long as the data, if advertised itself correctly as how it was collected and at what time it was collected, all those transformations can be automatically done, and there are software libraries to do that. But yes, there needs to be a more cohesive test bed, in my opinion, to show how all these things work together and how they can work together in far more computer-centric standards that maybe aren't the least bit worried about the spatial aspects, but have to adopt to them anyhow.
Yeah, it's just demystifying the problem, because while, there are a lot of additional things that we have to worry about when we, for example, define a geopose, we are designing it so that it is easy transformed into a geospace, and it can be represented easily in other software, and vice versa. So yeah, I think there is a lot more that we can talk about this, but it's an thing that I truly believe that we need that translation system between geospace and Euclidean space and make it even hardware accelerated.
That makes sense, Miguel. I see a question from Ajay.
Hi, Scott. I think I have no words to appreciate what you just said in the slides, and the reason is I am a person who worked with space agency in India and started working with space data for last 30 years, and now and I also worked on 3D data. I'm probably one of the pioneer from Asian region on 3D modeling cities, actually starting in Singapore. So with all that time, I really appreciate what you just mentioned. Maybe what I'm trying to say is all our metaverse discussions in many of the forums and groups which I am attending, there is a tendency to say that OpenUSD will be probably going to be the golden standard for everybody to jump in. But in reality, our world is a real world. Actually, there is no vacuum there. Whether it is in Earth or whether it is in Mars, there is no such real vacuum where you can say that my metaverse world is different from somebody else metaverse world, and then there is no need to talk about the real world. Actually, so I say we need to make sure that whatever meaningful standards we create, it has got some kind of an anchoring in terms of XY coordinate or a Z coordinate, whereas we can put that valuable data anchored to some coordinate. Actually, that's very, very important.
Mhm.
Once you make that anchoring, then you can make sure that it can be a wild dream or a scene which a creative mind wanted to create it and utilize it for some other entertainment purpose or gaming purpose or whatever it is. But having any amount of valuable data anchored into X, Y, and Z coordinate is a fundamental requirement. I think that's where the marriage of the entire metaverse discussion need to move towards. I think Scott is probably going to drive this discussion. I wish and pray for that. I wish everybody join hands with him and come up with a common direction for the metaverse discussion. Thank you.
Thanks, Ajay. And the one reason I sent a lot of people off to YouTube instead of paying attention to me is that there's a lot of complexity. There's a lot of work that's been done. There's ages and ages of trying to make digital representations easy to use. And in many ways, the more you try, the more you fragment the industry.
Yeah.
And I wanted to end on this slide with the GeoVolumes API, because I do think something akin to that, and probably not this particular API, is going to be necessary from a metaverse perspective to help ease the integration of information. And it may never be a standard. It may be instead a set of best practices where developers say, all right, I don't have to worry about Japan moving. Someone else will solve that problem for me. But here's the single library point of truth that's going to get me the answer I need to keep working on data that I'm doing over Japan. I still think we need more guidance, and we need it in the context and in the language that people that are working in the metaverse understand, because you just heard me speaking mostly in geospatial language, and some of you might go, but really, what is a coordinate anyhow? Your coordinates are different than my coordinates, and that can be a problem.
Okay, I'm going to jump in and pause the recording since we're at our time.